All right, that was more of a refresh of what you guys already know. So going on to address translation. So we talked about CPU virtualization, and the main strategy that we had was limited direct execution, LDE. For memory virtualization, we do something very similar. Just to achieve efficiency as well as control. For memory virtualization, we need some hardware support in the forms of registers, translation, leukocyte buffer, and page table. TLBs and page table we'll touch on more later in the course. But let's first look into address translation. So if you remember, the magic of OS is creating an illusion for each program to think they have the memory all by themselves, and their memory space starts from 0, etc., etc. So one of the key responsibility is a translation, right? So there's a virtual address space versus the actual real physical address. So to achieve these, OS still has to be involved at key points to set up the hardware and manage memory to intervene whenever it needs to. Now, just for the sake of explanation, we're going to go through some assumptions. First of all, the user's address space must be placed contiguously in the physical memory. The size of the address space is less than the size of physical memory, and each address space is exactly the same size. With that, let's look into the first example. So in a C language code, this is a very simple code. So what it happens here is that first, you load a value from memory, right? So you have X, then you load the value, and then you increment it by 3. Then, so this is the incrementation, then you store the value back into memory. So there were 3 steps involved. In the assembly, same. So if the C code basically, when it's changed to assembly, it will look something like this. So move long, right? So basically load 0 plus EBX into the EAX. Then you add 3 to the EAX register. And then you store EAX back to the memory, right? So that's the assembly code. So what actually happens in terms of address translation here is that, so we had these instructions, right? These assembly code, and these are the address. So first you fetch instruction at address 128, right? The move long instruction. Then you execute this instruction. Now here somehow it says you need to load address from 15 KB. Right? So that value was in the register. And then you fetch instruction at address 132. So here you just execute, you don't have to access the memory here. And then you have another move. So you fetch the instruction at address 135 and execute this instruction and store the address back at 15K. Right? So this was in the, so these are in the stack, right? All the variables that you have were in the stack. So in the physical memory, you have an operating system. It's possible you're not using certain parts. Now this program in the physical memory is from 32K to 48K, right, in the physical memory. But in the virtual address space, it starts from 0. The size of this block is 16K, right? So, you know, OS has to place this process somewhere in the physical memory, and most likely, definitely not starting from 0, because you have your OS running here anyways. So you're gonna need some help from the hardware registers. So we have a pair of registers, base and bounds. So here, base register is what it means is that in the actual physical memory, where does it start? Where is the base? So your 0 in virtual address in the physical real world, you start at 32. So there's the base, but there's also a size, right? Or the bounds or the limits. So here, the size is 16. Because you go from 32 to 48. So the base register will be 32. Bounds will be 16K. So when a program starts running, the OS decides where in physical memory a process should be loaded. And that's the base register. So here, physical address is basically virtual address plus base. Here, right, physical address is virtual address, let's say 0 plus 32. And every virtual address, obviously, must not be greater than bound. And it should not be negative. So let's look at example here. So at address 128, you have this instruction. So first you fetch instruction at address 128. So here you had a base of 32K, right? And you're in address 128. So this physical address of this instruction would reside in 32,896. So again, this is in the program code. And then you execute this instruction and it loads from address 15K, right? So you load it from here. So 15K plus 32K base, and that will be in the physical address 47K. Now, in terms of bounds register, there are two different ways of to actually write it. So one could say, hey, the size of this process address space is 16K. Or one could elect, oh, I actually want to explicitly specify the end of the address space in the physical address. So in this case, I started at 32, the limit is 16, so it'll be 48. So there are two different ways of actually stating the bounds. And I think the textbook actually sticks to this case, the actual limit, the size. There are a few more hardware requirements for this dynamic translation. One, just like in the CPU, there's a privilege mode. So this prevents user mode process from executing privilege operations. And as we looked at, we need base and bounds registers. You need a pair register per CPU to support address translation and bound checks. Obviously, you're going to need some ability to translate virtual addresses and check if within bounds limits. You need privilege instructions, meaning you need to be in a privileged mode to be able to actually update base and bounds, right? Because when you have to do context switching, right, you're going to have to update this. So hardware needs to support this. So OS must be able to set these values before letting a user program run. And also another privilege instruction to register. So OS should be able to tell hardware what exception handlers code to run when the exception happens. And of course, you can raise exceptions when a process tries to access privileged instructions or out of bounds memory. Now, in terms of OS for memory virtualization, so there are three critical points. So one is when the process starts running. So you're going to, first of all, have to find the space for the address space in the physical memory. And when the process is terminated, then you have to reclaim the memory. Right? So if the process is done, that process, the memory that process was using, now you want to take it back so that you can recycle it. Now the fun part is always when the context switch occurs, then you have to save the baseband bounds of the current processor. Then also you have to be able to load the baseband bounds of the new process. Because again, context switching, you might have to go back and forth or switch, so you have to maintain those values. Yeah, so just for each, so basically the first time when you're trying to find a room, you're going to have a list of the range of the physical memory which are not in use. So in this case, at the physical address 16K, this is free. At the 48K, this is free. So when a process is terminated, let's say this process A that was in 32K get terminated, then you need to add this back into the free list. In terms of save and restore, let's say process A currently running, the base with 32 bounds was 48. So what you're going to do is there is a data structure called process structure or process control block for each process. So you store that value. And now you're switching to process B, so your base and bounds need to be updated. So this is the role of the operating system when context switch occurs in terms of memory virtualization. Right, in terms of exception handling, again, similar to what we did for CPU, OS install the handlers at boot time. So for instance, when the segmentation fault happens, there's exception handling mechanism, probably kill your process, sends error message, and refresh, and so forth. Yep. Any questions so far? Yes. So in terms of base and bound, so base is basically like, so your operating system, where where not in use, right? Depending on your process size and all that, there's a limit on what's the largest memory block process can have anyways. So there's a limit on the bounds. But this is like you're deciding where you want to put. The operating system decides that. And sometimes, like you mentioned, different process might have different size. And we're going to talk about it in the next part right now in terms of segmentation. You're going to have to find the right spot, right? Because sometimes here the assumption was every process has same size, right? But not all processes might have the same memory size. Then you have to take that into account when you're actually putting it into the physical address.